Let's continue with the last session of this workshop. Now we will hear something about quantum distributed algorithms, about foundations, distributed algorithms, and non-locality in quantum networks. And the talk will be presented by Marc-Olivier Renou. And so the stage is yours.
Yes, thanks a lot. So first, thanks a lot for the invitation and the organizers of this nice conference in this very nice place. So today I will talk about some foundational questions about quantum distributed algorithms. So, okay, we know that we have a lot of potential future quantum advantages from quantum technologies. And then one question is, okay, how can we use or access to this in the future? And probably we'll use quantum networks. So for me, a quantum network will be a large system of geographically distributed and interconnected quantum information processing devices with photons which will carry the information. And then some applications are cryptography, secure remote quantum computation. Also, some people talk about solve the scalability issues of centralized quantum computing. So first, something that I would like to stress is that I'm not talking about that. So in distributed computing, often you separate in two. You have parallel computing, where the goal is to construct an efficient large computer. And then for some reason, you decide not to construct one large computer, but many tightly coupled computers. But then you also have distributed algorithms where the setup is quite different. You have to manage some distributed structure which is inherently distributed. So there you have to adapt your algorithms to the nature of the network you have. So in that case, you really decide that you want a network. In that case, it is just given by, well, the physics, the geography of it. Yes, so I'm really not talking about that. Okay, and then, so these quantum networks, they will support some applications. So for instance, quantum cryptography protocols, which is often involving two users, but actually they will be composed of many more users. So then the question is how to manage to have this 100 quantum network structure able to implement a lot of different cryptographic protocols like involving only two users, each of them, and how to make it so that everything works in parallel. So what if a processor fail? What if we have a lot of latency in the network? How to distribute the resource of that network? Okay, so the question I want to ask here is, well, could quantum information processing better solve these issues? So the goal is to find tasks, abstract tasks, where we will maybe find an advantage or not. And this will maybe guide the future development of quantum networks just by saying, okay, actually your quantum network can go faster for this or not. Okay, so first I want to introduce the model I will use and discuss in this talk, which is the local model. So here I will assume that the nodes are computers which have infinite computational power. I will also assume that communication is infinite bandwidth. And I will assume that what costs in the network are the communication. So the communication will be synchronous, but I want to avoid them as much as I can. Okay, so I will really concentrate on this issue of latency in the network. So this will be the cost that I want to minimize. So in the classical internet, actually in one communication step, you can do locally a very huge number of computations. So what is really the cost is the communication, and for most tasks, the local operations are costless. So you can assume locally that you have infinite computational power. So now the question is really, can a quantum network be more efficient than a classical one against latency for some problems? Okay, so what I will do is I will take a very basic abstraction of networks, and then I will try to find some quantum algorithms that go faster than classical ones for some tasks. So if you are familiar with Bell non-locality, you can really see this as a generalization of Bell non-locality, in which now, instead of having no communication between the parties, I allow for a few communication steps along a network. And also what is very important to understand is that the network structure in itself is unknown by the parties in advance. So you discover it through communication somehow. So in this talk, I will discuss 3 works. So in the first 2, I will show that for many natural problems, actually there is no quantum advantage, or essentially no quantum advantage. And then I will show that I can also find a task for which there is a clear quantum advantage when we consider this latency. So before going to these 3 works, I want to give a bit more intuition about the type of problem I'm interested in. So a very concrete problem is phones over France or over Europe selecting frequencies. So, if you have 2 phones connecting to a same antenna, they don't want to use the same frequency because they would be crosstalk. But 2 phones far away might use the same frequency. So here you really have a coloring problem. Each phone should select a frequency, a color, and nearby colors related in the network should be different. But then, of course, you don't have the time to send all the information about the full network of all phones to a centralized computer solving the problem and sending back the solution. You really need the phone to decide for themselves what frequency to use by communicating a few time steps around them, and that's it. Okay, so if you take that problem, and if I consider a very, very simple toy model, so now I will consider a line of 10 phones. I will assume that they have access only to 2 frequencies, 2 colors, and I will assume that they have time for only 3 messages due to latency. Okay? And it's synchronous, right? The messages are sent according to a clock. So what you can show very easily is that actually this task is completely impossible. And the proof of it will be very important for my first example, which comes next. So it's a proof by contradiction. So assume that you can. So there is an algorithm which works with 3 communication steps such that the color on the left and the right, so should be different, right? Because if you have 2 colors, you must alternate. Then, well, you can look at what would have happened if you had removed a node in the middle. So if you remove a node in the middle, you can again look at the extremum color. And what you can say is that the color outputted by this node can only be a function of what happened in this part of the network, because it goes only at distance c when communicating. So of course, what happens here and there should be exactly identical, and the same here and there. So if I have a combination of blue, pink here, I will also sometimes observe blue, pink in the 9-node network. But then, of course, in that case, you will have a problem because this is not well colored. Okay, so this type of arguments actually is something quite powerful, which can be used to bound what quantum can do. So now I will discuss first 2 results that we obtained recently, in collaboration with many people, which essentially show that for some tasks, some natural tasks, there is essentially no quantum advantage. So you cannot go faster using a quantum algorithm. And the first one is a coloring problem. The second is, a more general family of problems. So let me first discuss the first task. So the task is exactly this. So you tell to the node, I will connect you in a graph, and the node know in advance that the graph can be colored with chi colors. This is a promise. And then you ask the node to manage to color the graph with C colors, where C is larger than chi. Okay, so you are a node, you are connected to some neighbors. You know that the global structure can be colored with chi colors, and now you have a list of C colors you can use. And the question is now to minimize the number of communication you use to color that graph. And you could use quantum or classical communication. So what we have found is that there exists a classical algorithm which solves this task, let's say, pretty fast. Okay. And then also, any quantum algorithm requires the same number of communication steps to color up to some logarithmic factor. So the dominant term is the same. So there is essentially no quantum advantage. So I think I have a bit of time to give the proof ID to prove this kind of result. And actually, as you will see, it's quite the same as what I did with this 10 versus 9-line network. So I think it's good to understand the type of concept we manipulate. So to prove one, well, I won't do it, right? So you need to find the algorithm. This is a classical question, so I don't want to discuss it. But then for two, it looks quite hard, right? You want to rule out any quantum algorithm. How can you do this? So we do a proof by contradiction. We assume by contradiction that there exists a quantum algorithm which works in less than this number of time steps. And then it's a graph problem, actually. What we do is that we find what we call a cheating graph, which has some properties. So this cheating graph will then use it to cheat the node. So we'll pretend to the node that they are connected in a graph which is satisfying this property, but actually we'll cheat and we'll connect them in H and see what's going on and we'll find a contradiction. So this graph H that we managed to construct has two properties. So first, it cannot be colored with C colors for some global reason. This is a property we can show. And then the second property is that if you take in this cheating graph H two nodes, which are neighbors, U and V, then you can always find a graph G indexed by these two nodes which satisfy this property, which is in this family of graph, such that looking at distance t from these two nodes, either in H or in G, you see exactly the same. So the local structure of H and G around U and V at distance t is the same. So here in red, I took t equals 1. You see exactly the same, but then maybe at longer distance, right, the graph becomes different. Okay, so we are able to find such a graph. And why does it work once we have such a graph? Well, it works because now we imagine that we run the quantum algorithm, which by contradiction works in H. And what we say is that, well, what's happening for these two nodes, U and V, only depends on what are the nodes at distance t. So what happens here is exactly the same as what happens there for these two nodes. I assume that this was well colored, so this should also be well colored. And then actually I can do this for all pairs of nodes, right? So if I take another pair, I will find another graph because by like the property of that graph, it works. So I can show that any two consecutive pair of nodes are well colored in H. So I have just shown that H can be well colored in the end, right? Which is a contradiction because I know that H does not admit a C coloring. Okay, so this is a very generic proof technique, and indeed it's not genuinely quantum, right? It's valid against also no signaling strategies, so more powerful than quantum strategies. So then we were able to prove another property. So essentially what we prove is that for any local problem in rooted trees, which is a specific class of graph, if it can be solved very fast with a quantum algorithm, then it can also be solved very fast with a classical algorithm. So I don't want to specify exactly what I mean by this. I will keep this result at a high level. But what I want to specify is the class of problem we are considering, these locally checkable labeling problems. So typically these problems are coloring problems. But another problem, which would be that the sum of all outputs of all nodes is 0 modulo 2, is not a local problem, because this is a global property. So locally checkable labeling problems are really the analog of NP problems, so problems which are easy, which solution is easy to check, but for synchronous distributed computing problems. So typically in these problems, if you have a potential solution, to check it, you just need that each node look around itself at small distance and check the compatibility of its own potential output with its neighbor output. So a coloring problem is clearly like this. But there is no need to check at long distance. And if at the end the nodes are all happy, then we have solved the problem. So this is really the counterpart of NP problems, where it's easy to check that you have a solution once someone proposes one. And these are the problems which are interesting in this local model. Okay, so let me now discuss our third result. So in our third result, we have shown that actually, so the previous two results were saying essentially that, okay, for this or that problem, there is essentially no quantum advantage. So, okay, an open problem is, can you find a quantum advantage? So this is what we have found. And this is what we call a cascaded Bell game quantum strategy. Okay, so let me try to explain what is that game. So first, this game is in a degree delta graph. So we'll play in graphs of degree delta. And then, if you are familiar with the pseudo-telepathy GZ game, what will happen is that all the nodes will play a lot of this game in a cascaded way. Okay? And then what we have shown, so I will go back to what is the problem exactly, but first the result what we have shown is that for this game, there will be a one-time step quantum algorithm which will solve it, while for any classical algorithm, you will require at least deta time steps of communication. Okay? And this is also a problem which has a local winning condition. Okay, so I want to try to give you the flavor of the problem, how it is exactly. So I must go a bit fast, so I will assume a bit of familiarity with the GZ Bell game. So if you are not familiar at all with this, you can just rest a bit and come back with me in 2 minutes. Okay, the CHSH game is this game where Alice and Bob have two inputs, X and Y, the output A and B, and then you have A plus B modulo 2, which is equal to X dot Y with a very high probability. So if you want to solve this classically, you can only achieve this 3/4 time. Quantumly, you can go higher, and in no signaling, you can do with 100% probability. So while our initial game is about the GZ pseudo-telepathy game, I will just give you a flavor of it by just assuming that quantum mechanics allow us to solve this with 100% probability. Okay? And then actually it's not the case. So what we did was to adapt what I will tell you to the case of GZ, where quantum mechanics can really win with 100% probability. But already this will give you a very good flavor of what we have done in our work. Okay? Let's assume that quantum mechanics win that game with 100% probability. So let's assume we have what is called a Pierre box. And let me show you what is this one-time step quantum strategy with these special CHSH quantum boxes. So imagine you are a node in this network, and imagine delta is equal to 3. You have 3 neighbors like this. And what is given to you actually in the problem also is that these are labeled from 1 to delta. And then what do you do in this one-time step quantum algorithm? Well, so in one communication step, you just establish maximally entangled state phi plus connection with your neighbors. So this is easy to do in one time step. And then you don't have any more communication step. You just do the following. You input 1 in the first CHSH box you have, and you obtain an output A1. And then you use this output A1 as an input for the second CHSH gain, and you obtain an output A2. And then you use it in the third, and you obtain an output A3. And then, well, if it's delta, you do this delta time. If it's 3, you are done. You just output A1, A2, A3. And this is it. Okay? And then, so what we managed to do is to show that this actually, to reproduce it, classically, you need like delta time steps. Okay? I'm done almost with my talk. I wanted to finish with some open problems, which I find interesting in these foundations of distributed problems, and do quantum help to solve them? Yes, so the first one is about coloring a loop of nodes, where, as I will tell you, it's completely open. And a second one is about Byzantine agreement problem, and it is, do quantum tolerate more faulty nodes when we look at these consensus problems? Okay, so my first open problem is the following. So I take exactly the same setting as the one I described, so synchronous communication, a network, and you want to solve a task as fast as possible. So now the task is coloring a loop with C colors, okay? So you imagine that you have a loop of nodes, n nodes. They don't know in advance where they are placed in this loop, and they should exchange messages and color the loop. So what is quite well known classically is that, so above 2 colors, if you have 3 or 4 or more colors, the number of time steps is something which is called log star of n, where n is the size of the loop. So this goes very slowly, but still it goes to infinity as n goes to infinity. And then, well, for quantum mechanics, it's not known at all. But what we can try to do is to use the same type of argument as what I used in my first example, where I used this cheating graph H, and try to find some no-signaling bond on quantum mechanics. And then actually what you can show is that the best bond you can find using this type of argument is only 2 for 3 colors and 1 for 4 colors and more. So if you want, with what we call peer boxes, this no-signaling box, there is no way to rule out the fact that it can be colored with 2 time steps only, even if you have millions and millions of nodes in your loop with 3 colors, or even 1 with 4 or more colors. So then the question is, okay, where does quantum stand? And maybe quantum allow to color a loop in a finite constant number of time as n goes to infinity. And more generally, actually, the method I have presented with this cheating graph, which is indeed no signaling, is the unique method which we know to bound what quantum mechanics can do. So the question is, how can we mathematically prove separation between these two models for concrete problems? It's open. And in that case, it leaves this question open. Okay, and then the second open problem I had in mind is the following. So now I go to a different type of problem, which are these consensus problem in which some nodes are not acting as they should. So for the famous Byzantine agreement problem, you have this 1/3 like threshold. Below 1/3, you can find a Byzantine agreement. Above 1/3, you cannot. And then it's easy to show, to see that proofs of this statement are also quantum valid. So for this specific problem, quantum mechanics do not enable to tolerate more Byzantine nodes. But what is done to my best knowledge is, can we find another consensus problem where classical information theory, classical algorithm enable us to tolerate some number of failing nodes, Byzantine nodes, and quantum mechanics allows for more robust algorithm in which we would have more potential Byzantine nodes. Okay, so with this, I'm done. So we are a lot of authors in all these papers, so I have a lot of pictures of probably not all the authors. It's found with ChatGPT. And this is so my group in INRIA Saclay. So part of us are working on these questions. In particular, Isadora Veren and Lucas Stendik, who are co-author of the last paper, and also Luis Fateme, Carlos, Amanda are working on that. Thank you.
Okay, thank you. Are there questions or comments?
Thanks, Marc-Olivier. It's more a question about when you say quantum here, you say quantum with a local model, right? Or implicitly, right? But this model, if it's correct, it doesn't take into account loss, right? You assume that...
So I take a extremely abstract model, which is ideal, right? So there is no loss, so you can distribute entanglement as much as you can. The goal is really to find because if I find a limit on the quantum model in that case, it's a very hard limit. For sure, you won't be able to do this even if you have ideal model with no loss, etc. And then if I find a concrete algorithm where I have a quantum advantage, then you can look very concretely at this algorithm and ask yourself, is it realistic to do that with loss and stuff like this?
Yeah. But I'd like to push a bit the argument. So your example of internet is convincing, but in classical communication, when you send a communication, it always arrives. In quantum communication, this is very different, right? So when you send a photon over 100 kilometers, it rises 1% of the time. So it's so do you think there is a hope to bridge this gap to also include parameters like loss in this kind of works?
Yeah, well, so you see the concrete algorithm that I propose, which is not completely this, but looks like this, right? Look quite cheap actually, right? I'm not asking any entanglement swapping or very crazy things, right? I just ask to have phi plus connection established between any consecutive nodes, right? So, well, in the end, we obtain a very abstract problem, right? So we can show that for a very abstract problem, there is a quite clear quantum advantage. So then a question is this any useful, this abstract problem, right? But then you can also look at the quantum algorithm we are using, and it does not look crazy, at least to me, right?
Very nice talk. I really enjoyed it. Thank you. I have nothing to add except for there is a whole sub-area of quantum error correction algorithms, which I don't know, they look the same. I don't know whether Matthew has any insight into this or not. I mean, there are graphs and the coloring problems, I think, that are extractable from it. So I guess on a question, maybe it's a question, have you looked into that? And if you haven't, you might want to consider looking at the LDPC, on what DPC codes and maybe proven properties of them, which are not readily apparent to the coding people who just don't care about this kind of stuff. A very nice talk.
I guess I have no answer, right? The answer is no, I did not look into this, right? So I will discuss with these people, yeah. Yeah, no, I know what it is vaguely.
Yeah, but there's embedded graphs in them, and there are also embedded coloring problems in them. So put two together, add your work.
Yeah. Well, it's not so clear to me how connected it is to our model. I have to look into it, yes.
For the talk, I wanted to ask for the first open problem, is it as difficult as finding can you apply directly a Bell-like inequality? There are inequalities for bounding the sets? No, because then you have...
Well, maybe, but nobody found it.
Okay.
And I doubt, but...
Okay, then thank you again.